that you know the basics of circular motion, like what is centripetal acceleration, what is centripetal force. So the question is, in the situation shown, the gramophone record is rotating at 30 revolutions per minute. So what is this situation? This is a death well. Okay, can you imagine what is a death well? What is this situation now? A car is taking a turn. So now understand one thing, it doesn't have to be a complete circle. If we are already knowing that the road has to curve like that, why not bend the road? Hello students, welcome in today's class. Today's class we are going to talk about banking of roads or tracks. This is a very important topic as many questions are directly asked from this particular topic. So you should understand this really well. One more thing, this is related with circular motion. So I would expect that you know the basics of circular motion, like what is centripetal acceleration, what is centripetal force, what is centrifugal force. So all these things you should know, only then you would be able to understand this class. Alright, so I think we can start. So the first thing that I wish to talk about is a question. So let's start away, right away with a question that will give you a clear picture what we are going to do today. So what is this question? Please note it down first and then I will start. Alright, so the question is, in the situation shown, the gramophone record is rotating at 30 revolutions per minute. If the coefficient of friction between the coin and the record is 0.5, then find the maximum radius in which the coin can revolve. Alright, so let's quickly understand what is this situation. This is a rotating gramophone record, and as this is rotating, this coin placed on the record should also rotate with it. Alright, so let's draw the free body diagram very quickly. So let me show the forces. Obviously the two basic forces that you would think of is mg in the downward direction. I am drawing the free body diagram of the coin, and the normal reaction acting in the upward direction. So these are the two forces that are acting on the coin in the first place. Now when this coin is when this gramophone record is rotating, the coin also needs to revolve, right? And if it has to revolve, it has to move on a circular path, and for a circular path what we need is a centripetal force. What we need is a centripetal force. Who is going to provide that centripetal force? The answer is going to be friction, right? So can you imagine that when this gramophone record is rotating, the coin is also revolving with it, and friction is helping it to revolve like that. So what are we asked here? What is the question asking? That what is the radius up to which this coin can revolve? Alright, so let's do one thing first. The value of omega is 30 rpm, that is revolutions per minute. So first let's multiply it by 2 pi, because you do understand one rotation is like 2 pi radian, and divided by 60 to convert that to per second. So it is per minute, I have to convert that to per second. So when you do that, it is turning out to be pi radian per second. Alright, so I have converted omega into pi radian per in radian per second, which is pi radian per second. Now understand, n is equals to mg, but of course it is very easy. This is the equation in the y direction. In the y direction the net force is 0, so n is equals to mg. Now in the x direction, if this coin is revolving, friction is helping it provide that centripetal force. So in the x direction I should write friction is equals to m omega square r, as you would know. But now understand, if we talk about more radius, then we need more friction here. For more radius we need more friction, because omega is fixed. What is fixed? Omega. So can we say, let's say this is omega, okay? So omega is fixed. So for this given omega, if the radius increases, the coin will need higher centripetal force. So that is why if I take the maximum value of radius, I will need the maximum value of friction also. Now understand, what is the maximum value of friction? Of course you know that. So it is mu n, that is the limiting value of friction. So that is why, if you can see, the question has not given us the mass of the coin because it's not needed. So because the term of m will cancel out. Now all we need is the radius. Okay, so mu is how much? Mu is 0.5. Okay, g omega square is going to be pi square. Okay, and r max. So if you know that pi square value is also approximately 9.8, so we can cancel pi square and g. So r max turns out to be 0.5 meter, or you can put it as 50 centimeter. So up to 50 centimeter this coin can revolve, but more than 50 centimeter this coin will slip. It won't be able to maintain on that circular path. Understand this. What do you mean by slipping? What do you mean by centrifugal force? So the coin has to rotate, let's say like this, but if friction is unable to provide that centripetal force, so what will happen is that coin will not be able to maintain on that circular path. So when it is unable to maintain in that circular path, it feels as if the coin has moved away. It has moved away from the center. This is in a way the feel of centrifugal force. Centrifugal force is no force. It is just like it is an illusion. When the coin is unable to maintain on the circular trajectory, it feels as if it has slipped away from the center. That is what is called centrifugal force. So sometimes people do it like that, that instead of showing this as a centripetal force, what they do is they show it as a centrifugal force, that this is, let's say, a force acting outward, m omega square r, and then what they do is they balance off friction by m omega square r. So that is like a pseudo force. If you don't know what pseudo force is, then you should go and watch our pseudo force class where we have discussed all about pseudo force. But the thing here is that this numerical is a classic way of understanding how anything revolves in a circular path on a uniform circular motion, and that is the dynamics of it and how the forces are involved. Here N is balancing mg and friction is the provider of centripetal force. Alright, so it was easy. Copy this down, then we move forward. Alright, so the next thing, again let's take one more question just to do vice versa now. So in this situation, find the minimum speed with which the car should move so that it does not fall. So what is this situation? This is a death well. Okay, can you imagine what is a death well? So it's a well and cars have to move with some particular speed to maintain on that circular trajectory, and if they slow down, in fact then they will fall. So in the previous case, if the the rotation speed of the coin increases, then it will slip. Here they will slip if they will slow down. Let's understand how. Okay, so let me draw the free body diagram of this car. So let's say this is the car here. Okay, I am drawing it separately. So what is the force acting downward? Mg. Can you imagine? This is the wall, this is the car, Mg is acting downward, but this time the normal contact is provided by the wall. Okay, and if the car will slip due to its own weight, so can you imagine the car will slip due to its own weight, so to counter that, friction is acting. To counter that, friction is acting. So that's how things are. Mg is acting downward, N is acting perpendicular to the surface, and friction is actually stopping it from slipping or falling down. What would you say? Now you would say that if it is moving on a circular path, obviously it is moving on a circular path, so in x direction first, N will be equal to mv square by r. Of course, yes. Now N is the provider of the centripetal force. Here N is acting. This N is rotating this in circular path. Alright. So in y direction, if we want this car to remain stable and not slip, we would want the limiting value of friction should be greater than equal to mg. Why? Because mg is wanting this car to slip down. The weight is wanting this car to fall, but friction is stopping it from falling. So the limiting value of friction, that is the maximum value of friction, should be greater than mg. So can I write mu n should be greater than mg, and in place of n this time I would write mv square by r. Okay. So this should be greater than equal to mg. The term of m again cancels out, so we don't need the mass of the car. So v should be greater than or equal to rg by mu. V should be greater than equal to rg by mu. You can do the calculation very quickly. So v should be greater than equal to, what is the radius of the death well? It is, let's say, 5 meter. Let's take the value of g as 10, and this is like 0.5. Okay. So what is this value turning out to be? So this will be, I think, 500. Sorry, 100. V will be greater than equal to root 100. So that means V is greater than or equal to 10 meter per second. So this car needs to now move with a speed greater than 10, not less than 10, because if it goes less than 10, then it will of course slip and friction won't be able to sustain the weight of the car. So are you understanding how the dynamics are of any circular motion, how the forces are operating? In the previous question, let's look at it again. N was countering mg and friction was providing centripetal force. Now N is providing centripetal force and friction is countering mg. So it's such a wonderful contrast of things. Alright, you can copy this down. Now we start with the topic. Alright, so now let's move forward. Okay, so what is this situation now? A car is taking a turn. So now understand one thing, it doesn't have to be a complete circle. Even if you are like turning, that is part of a circular trajectory only. Just like the concave, convex mirrors or lenses that you might have studied in your previous classes. So a concave mirror like can be a spherical mirror, but it does not have to be a complete sphere. It can be a part of a sphere. Just like that, if you are turning like this, can you understand? This is a road and you are turning like this. Even then this is a part of a circular trajectory. Even then you are, requiring the centripetal force or acceleration to take that turn. So let's say this is the radius in which you are turning, and then again the situation is going to be that mg is going to act in the downward direction, n is going to act upwards, and friction is going to provide the centripetal force, isn't it? So very easily what we have done here is that we are talking about turning of a vehicle. So it is like turning. So this vehicle is, this is the back view of the car and it's turning on a road. The road is turning itself and the car is following that path. So it's part of a circle. Okay. And what are we finding here? Let's find maximum permissible speed. Maximum permissible speed. All right. What are we trying to find here? Maximum permissible speed. So what will we do? In the y direction, we will write n is equals to mg, but of course, and in x direction, we will write that friction is the provider of the centripetal force. So there is no problem. Friction is a self-adjusting force. If you are turning at a lower speed, there is no problem. When is the risk? When you turn at a high speed, because then the friction won't be able to provide you that centripetal force. So there is a limit that friction can achieve, that is the limiting friction. So there is a limit that at this particular radius you cannot go beyond that speed. How will you determine that? So let's remove this for once. Okay, so let's write friction when achieve its limiting value, that is the maximum possible value, then we will call this as mv max square by r. And what is the limiting value of friction? So the answer is going to be mu n. The answer is going to be mu n. All right, and n is equals to mg. So what would you write? So it is very similar to the coin situation, but now it's a car, that's all. Okay, and now we are rather talking in terms of v than omega. Okay, m cancels out, so v max now turns out to be under root of mu rg. So this is turning of a vehicle on a level road, on a horizontal road. There is a turn and the car is turning with that. So this is the maximum speed that you can have. If you go beyond this speed for this particular coefficient of friction, then the car won't be able to take the turn. It will slip off. It will feel as if it is unable to maintain that circular path. Now there are only two choices. Then mu has to increase. If mu increases, then you can take the turn at higher speed, or if the radius increases. So that is why if you turn in a bigger radius, that is less curvature, then you can turn at higher speeds also. But if you have to turn in a smaller radius, that is more curvature, then your speed has to be slow if you want to, or less if you want to take that turn. Very easy, no big deal. This is turning off a vehicle on a level road. You can write down what have we derived. We have derived the maximum permissible speed for this particular situation. Okay, so you have to pause the video and copy it down. Next, what do we do now since friction has a limit? So if we are already knowing that the road has to curve like that, why not bend the road? Why not bend the road? What advantage does it have? So this is what we call as banking of roads. Okay, this is what we call banking of roads. So what are we doing here now? We are going to bend the road itself. Not we, but the civil engineers who's going to construct the road. If they already know that the turn is like that, why not bend the road? What advantage will it have? Imagine. So you would say now N will be like this because you're pushing the road like this, but we are not bending it so much that it's even more than the angle of repose and the car starts slipping. Not that. It's just that we bend it slightly, let's say 5, 7, 10 degrees, so that the normal reaction becomes oblique, and we can have a component of normal reaction also supporting you to take the turn. Otherwise you will only relying on friction, but now even component of normal reaction is going to help you take that turn. So that is the whole idea, that we bend the road purposely so that the normal reaction becomes tilted or oblique, and you will have two components of normal reaction, that is y component and x component. Needless to say, friction is also there. We are not denying that friction is also there, but a support of normal reaction is way bigger. That's why bending the road itself or banking the road itself is very, very, very crucial, and especially in case of highways where you are not willing to lower down your speeds. So it's very important for the road to be bent like this so that you can even take turn at higher speeds. But let's do the physics of it. You can just look at it and then I move forward. So the physics of it, I will draw this the back view of the car and make it simple by drawing the two-dimensional diagram for you. So what are the forces acting very quickly? So you would say that mg is going to act in the downward direction, n is going to act perpendicular to the surface, and friction is going to help you take that turn. All right, so we are talking about taking turn at high speeds. That's why it has a tendency to slip here and friction is acting down. You can take it like that, or you do understand that friction is actually the provider of the centripetal force, so it is acting here. Okay, so let's do one thing. Let's resolve the forces in y and x direction very quickly. Okay, so this angle is theta, so this angle will also be theta. This is 90 minus theta, so this again would be theta. So the components of m, let me take another, components of n would be n cos theta here and n sin theta here. But of course, similarly, components of friction, if you are paying attention, components of friction would be f cos theta and f sin theta. All right, f cos theta and f sin theta. mg, I think all the forces are done, friction, normal reaction and mg. These are the only three forces: weight acting downward, normal reaction acting perpendicular to the surface, and friction acting parallel to the surface. All right, so now let's do the physics of it. First, consider the y direction. All right, y direction. What are we going to write? n cos theta, alright, is equals to F sin theta plus mg. Upward force is equals to downward force, or what we can write is mg is equals to n cos theta minus F sin theta. That's our first equation that we have written in the y direction. Now let's talk about x direction very quickly. Are you visualizing this? That apart from the component of friction, now we have component of normal reaction also. So bending it like this is very important. Like for example, if you have seen cycle racing, there's a term called velodrum for the cycle racing tracks. They are so much bent because you don't want to lose that thrill. You want the cycle speed to be really high, and that is why they bend the tracks like that. Okay. So now let's quickly talk about x direction. What are we going to write? We are going to write F cos theta plus n sin theta equals to mv square by r. So let's say this is a radius, okay, as you have seen in the previous diagram. Let's say this is the radius of the turn, okay, r, in which it is turning, okay. So is equals to mv square by r. Net force towards the center is mv square by r. What are we going to do? Let's call this equation 2 and divide equation 1 by equation 2. What are we trying to do here? We are trying to calculate the maximum permissible speed. That's the idea. So let's divide, m cancels out, so v square by rg becomes equal to what? F cos theta plus n sin theta over n cos theta minus f sin theta. You can memorize it like that, or what you can do is you divide the numerator and denominator by cos theta. So then this will look like what? V square by rg equals to f plus n tan theta over n minus f tan theta. So what have I done here? I have divided the numerator and denominator by cos theta. Now forgive me for this, but I am writing it here. So the maximum permissible speed, when velocity becomes maximum, you cannot go beyond that. That means when velocity becomes maximum, friction also becomes maximum, because that is the only force that can adjust. Rest n cannot change, mg cannot change. The only force that can change is friction. So the maximum value of friction, of course you do know, is how much? Mu n. Is how much? Mu n. So I will put the value of f as mu n, and if I put the value of f as mu n, n will cancel out from numerator and denominator, and what are we getting? Rg, okay, I have written f as mu n, so this will become mu plus tan theta over 1 minus mu tan theta. That is the idea. This is the maximum permissible speed that is allowed for this particular road when this is the coefficient of friction. You must wonder one thing here, that you can take the turn here even without friction. Imagine, what if n sin theta itself is capable of giving you the turn? Then you won't need friction. That is where the wear and tear of the tires is going to be, or the wheels is going to be minimum. So do understand that what is going to happen if you take the turn without the help of friction. Let's understand how. So let's say this was n very quickly and this was mg. So what am I trying to do here? So if you have just seen, the component of n along the horizontal was n sin theta, and this component is n cos theta. So understand, if I write n cos theta equals to mg, and n sin theta is the provider of the centripetal force, so that should be mv square by r. So can I write, if I divide the two equations this time, tan theta is equals to v square over rg, or v is equals to under root of rg tan theta. So you can call it as the speed for which the road is banked. like this is the optimum speed, this is the ideal speed with which the vehicle should travel on this road, and there won't be need of any friction and you can take the turn without any wear and tear. So this is sometimes also called the optimum speed, okay. So this is something very interesting, that you can take the turn without friction, all thanks to the tilt of the road. Because of the tilt, n component we also have along the horizontal, alright, along the horizontal. This angle was theta, and I hope you are understanding the component. This is n cos theta and this is n sin theta. N sin theta is providing the centripetal force and n cos theta is balancing the weight. In fact, I have a very similar situation for you very quickly. If you can copy this down and then we move forward, but I would like to remind you again, keep this formula in your head. You can memorize this formula because many numericals would be like this, where this formula is directly used, and we'll do the numericals also. We'll share some question banks also with you regarding these topics, but you should first understand the physics of it, that what is exactly the thing that is happening here. So you can copy this down. I will wait here and you can pause the video and copy this down, and now you can take a screenshot of this as well. All right, so this is what I was talking about, the bending of cyclists. So of course bending of cyclist. So this choice, this choice is normally only with the two-wheelers. Four-wheelers normally don't have that choice, though even you might have felt it sometime, that if you take a turn at a very high speed, maybe your outer wheels might just lift off the ground, but that's a very rare scene. It might be happening in movies, but in practical life it normally does not happen. So but this choice is with the cyclists, that even if the road is not bent, they have a choice to bend themselves. So that is what you call as, so if this is a turn, the cyclist can bend himself like this, okay. So let's say this angle is theta, okay, the bending angle. So now by bending, what they have done is they have pushed the ground, like this. So they are getting the reaction like this, alright, they are getting the reaction like this, while mg is still acting in the downward direction, though it should be shown at the center of gravity, but right now for simplicity I am showing it here. So mg is still acting downward, but now they are getting the reaction force like this. It is a combination of friction and normal reaction, okay. So now you can resolve, so this will be r cos theta and this would be r sin theta, this will be r sin theta. So r sin theta is going to provide the necessary centripetal force, just as we did. So r cos theta is equals to mg, while r sin theta is going to be the provider of centripetal force. So by bending, what they have done is they have again achieved a component of contact force, normal contact force along the horizontal, and therefore provider of centripetal force. So if you divide the two equations very quickly here, 2 divided by 1, then what are we getting? Tan theta is equals to v square over rg, that is v is equals to under root of rg tan theta. You can call this as the angle of bending. So if you want to take a turn at high speed, you need to bend more. So if v is more, then theta is more, and that is what you might have seen in case of motorcycle racing. So what motorcycles do is, the motorcyclists, they bend so much that even their knee is about to touch the ground, and that is why they wear some knee protection to in order to avoid any injury of that matter. So for bikes, they keep their center of gravity low already, so their height is already low, and when they bend, so it is a very much probability that their knee might touch the ground. So that is where you cannot give up on the speed, so you have to bend even more to take that turn. So this is one more way of achieving turns at higher speeds. Even aeroplanes will have to do that. Even aeroplanes, while they are taking a turn, they also need to bend. They cannot take a turn like that. So this is very crucial. I hope circular motion we have been learning, but how exactly circular motion we are experiencing in day-to-day life, I hope you were able to understand. This was my effort to make you understand all this. I hope you have enjoyed this class, and if you've understood this really well, you should be able to do the numericals. But that's all for this particular class. Thank you. Bye bye. Happy learning. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.